Hello everyone, my name is Ninya May Akas and my report is all about reactions of aldehydes and ketones. Aldehydes and ketones undergo a variety of reactions that lead to many different products. The most common reactions are nucleophilic addition reactions, which lead to the formation of alcohols, alkenes, diols, cyanohydrines, and imines. Reactions of carbonyl groups. The main reactions of the carbonyl group are nucleophilic additions to the carbon-oxygen double bond. As shown below, this addition consists of adding a nucleophile and a hydrogen across the carbon-oxygen double bond. Due to the differences in electronegativities, the carbonyl group is polarized. The carbon atom has a partial positive charge and the oxygen atom has a partially negative charge. Aldehydes are usually more reactive toward nucleophilic substitutions than ketones because of both steric and electronic effects. In aldehydes, the relatively small hydrogen atom is attached to one side of the carbonyl group, while a larger R group is affixed to the other side. In ketones, however, R groups are attached to both sides of the carbonyl group. Thus, steric hindrance is less in aldehydes than in ketones. Electronically, aldehydes have only one R group to supply electrons toward the partially positive carbonyl carbon, while ketones have two electron-supplying groups attached to the carbonyl carbon. The greater amount of electrons being supplied to the carbonyl carbon, the less the partial positive charge on this atom and the weaker it will become as a nucleus. Addition of water. The addition of water to an aldehyde results in the formation of a hydrate. The formation of a hydrate proceeds via a nucleophilic addition mechanism. The first step is water, acting as a nucleophile, is attracted to the partially positive carbon of the carbonyl group, generating an oxonium ion. Second, the oxonium ion liberates a hydrogen ion that is picked up by the oxygen anion in an acid-base reaction. Small amounts of acids and bases catalyze this reaction. This occurs because of the addition of acid causes a protonation of the oxygen of the carbonyl group, leading to the formation of a full positive charge on the carbonyl carbon, making the carbon a good nucleus. Adding hydroxyl ions changes the nucleophile from water, a weak nucleophile, to a hydroxide ion, a strong nucleophile. Ketones usually do not form stable hydrates. Addition of alcohol. Reactions of aldehydes with alcohols produce either hemiacetals, a functional group consisting of one OH group and one OR group bonded to the same carbon, or acetals, a functional group consisting of two OR groups bonded to the same carbon. Depending upon conditions, mixing the two reactants together produces the hemiacetals. Mixing the two reactants with hydrochloric acid produces an acetal. For example, the reaction of a methanol with ethanol produces the following results. A nucleophilic substitution of an OH group for the double bond of the carbonyl group forms the hemiacetal through the following mechanism. First, an unshared electron pair on the alcohol's oxygen atom attacks the carbonyl group. Second, the loss of a hydrogen ion to the oxygen anion stabilizes the oxonium ion formed in step 1. The addition of acid to the hemiacetal creates an acetal through the following mechanism. The first step, the proton produced by the dissociation of hydrochloric acid protonates the alcohol molecule in an acid-base reaction. Second, an unshared electron pair from the hydroxyl oxygen of the hemiacetal removes a proton from the protonated alcohol. Third, the oxonium ion is lost from the hemiacetal as a molecule of water. Fourth, a second molecule of alcohol attacks the carbonyl carbon that is forming the protonated acetal. And lastly, the oxonium ion loses a proton to an alcohol molecule, liberating the acetal. Stability of acetals. Acetal formation reactions are reversible under acidic conditions but not under alkaline conditions. This characteristic makes an acetal an ideal protecting group for aldehyde molecules that must undergo further reactions. A protecting group is a group that is introduced into a molecule to prevent the reaction of a sensitive group while a reaction is carried out at some other site in the molecule. The protecting group must have the ability to easily react back to the original group from which it was formed. An example is the protection of an aldehyde group in a molecule so that an ester group can be reduced to an alcohol. In the previous reaction, the aldehyde group is converted into an acetal group, thus preventing reaction at this site when further reactions are run on the rest of the molecule. Notice in the previous reaction that the ketone carbonyl group has been reduced to an alcohol by reaction with lithium aluminum hydride. The protected aldehyde group has not been reduced. Hydrolysis of the reduction product recreates the original aldehyde group in the final product. Addition of hydrogen cyanide. The addition of hydrogen cyanide to a carbonyl group of an aldehyde or most ketones produces a cyanohydrine. The mechanism for the addition of hydrogen cyanide is a straightforward nucleophilic addition across the carbonyl carbon-oxygen double bond. The addition of ylides or the Wittig reaction. The reaction of aldehydes or ketones with the phosphorus ylides produces alkenes of unambiguous double bond locations. Phosphorus ylides are prepared by reacting a phosphine with an alkyl halide, followed by treatment with a base. Ylides have positive and negative charges on adjacent atoms. The following illustration shows the preparation of 2-methylbutene by a Wittig reaction. Addition of organometallic reagents. Grignard reagents, organolithium compounds, and sodium alkenides react with formaldehydes to produce primary alcohols, all other aldehydes to produce secondary alcohols, and ketones to produce tertiary alcohols. Addition of ammonia derivatives. Aldehydes and ketones react with primary amines to form a class of compounds called imines. The mechanism for imine formation proceeds through the following steps. First, an unshared pair of electrons on the nitrogen of the amine is attracted to the partial positive carbon of the carbonyl group. Second, a proton is transferred from the nitrogen to the oxygen anion. Third, the hydroxy group is protonated to yield an oxonium ion, which easily liberates a water molecule. Fourth, an unshared pair of electrons on the nitrogen migrate toward a positive oxygen, causing the loss of a water molecule. Fifth, a proton from the positively charged nitrogen is transferred to water, leading to the imines formation. Imines of aldehydes are relatively stable while those of ketones are unstable. Derivatives of imines that form stable compounds with aldehydes and ketones include phenylhydrazine, 2 and 4-dinitrophenylhydrazine, hydroxylamine, and semicarbazide. Oximes, 2 and 4-dinitrophenylhydrazones and semicarbazones are often used in qualitative organic chemistry as derivatives for aldehydes and ketones. To further understand the topic, here is a video explaining the reactions of aldehydes and ketones.
Alright, first, before we actually do anything, we're adding nucleophiles to the carbonyl. So we're going to have a carbonyl, whether it's an aldehyde or a ketone, makes really no difference. But what happens is that the carbon of the carbonyl is partial positive. So it attracts nucleophiles. And when the nucleophile attacks, of course, you cannot have a 5-bonded carbon. So you need to break the double bond. And when you break a bond, you give the electrons to the most electronegative element. In this case, it's going to be the oxygen at the top. And you're going to now get a nucleophile attached to a tetrahedral carbon, and at the very top I have an oxygen that right now it's negative. This intermediate right here is the intermediate that we arrive at anytime we attack any carbonyl. So we're going to call it the tetrahedral intermediate. And when you get a tetrahedral intermediate, you check to see if you have good leaving groups. And this one doesn't happen to have any good leaving groups. Carbons, these are 2 CH3s right here, are going to be bad leaving groups, and the nucleophile that we just added, we're going to assume that it's also a bad leaving group. So since you don't have any bad leaving groups in solution, then the oxygen is going to pick up a proton from water or from maybe hydronium if you add a little bit of acid. So it picks up a proton, and we end up with an alcohol. So that's what we're going to see in these reactions when we attack the carbonyl of the ketones and the aldehydes. The first reaction we're going to do is a reduction with lithium aluminum hydride. And lithium aluminum hydride has 4 hydrides, and it's a very strong reducing agent. When you actually use lithium aluminum hydride, you have to keep water out of it. So the first step, you just add the lithium aluminum hydride in an ether solvent, and then at the very end of the reaction, you're going to do what I like to call the quenching, people like to call workup, but we're going to be adding water, and that's where the hydrogen on the oxygen is going to come from. So the hydride is going to be a hydrogen that has 2 electrons, and a simplified mechanism, of course, would be a hydride attacking the carbonyl, forming the tetrahedral intermediate. And if you form the tetrahedral intermediate in this particular case, you would have 2 carbons, or maybe a carbon and a hydrogen, and we just added the hydride. This is the hydride from the lithium aluminum hydride, and then nothing can leave. So the next step would be, when we add the water at the very end, the oxygen picks up a proton from the water. So this hydrogen right here on the oxygen came from the water. This hydrogen came from the lithium aluminum hydride. Now this is a very simplified mechanism that doesn't take into account what the aluminum or the lithium are doing. But we also have a second hydride reagent, not as strong as lithium aluminum hydride, but quite useful nonetheless. It's sodium borohydride. We have seen it before in 3331, but now it's a much easier reducing agent to use. I don't need to have 2 different steps, and I don't need to have syringes for this reaction. Sodium borohydride can be used in an alcohol, and we see exactly the same thing. The hydride is going to be attached to the carbon, and this hydrogen right here came from the alcohol. So whatever alcohol you're using, it's gonna provide the hydrogen that goes on the oxygen. So we have 2 reducing agents: lithium aluminum hydride, incredibly strong reducing agent. Sodium borohydride is only good for ketones and aldehydes. So in that sense, it's a selective reducing agent. I have some examples right here just to make sure that we understand that lithium aluminum hydride and sodium borohydride react with carbonyls. So I have a double bond right here on the left. I am not going to be touching the double bond. It's going to remain in place. Lithium aluminum hydride can only reduce the ketone. This is a ketone, so I reduce a ketone to a secondary alcohol. This is another ketone. I'm using sodium borohydride. Notice that I still have an alcohol. This one is ethanol, but all I'm going to be doing is reducing the carbonyl. I'm not going to touch anything else in the molecule. The one at the bottom is an aldehyde. And notice that I have an alcohol on the left. Lithium aluminum hydride can only reduce the carbonyl. So it will take that aldehyde to the primary alcohol. So aldehydes are reduced to primary alcohols. Ketones are reduced to secondary alcohols, and we have 2 examples of that. Alright, this is one of my favorite reactions. It's the addition of a Grignard or an organolithium, if you have it, to a carbonyl. And the Grignard is a carbon that's actually negatively charged, and it's basically a salt of magnesium. So I have two negative charges, and I have my magnesium in the middle between them. But what's important again is that the carbon that's attached to the magnesium, that's a nucleophilic carbon. It has a negative charge, so it will attack the carbonyl. It will form a tetrahedral intermediate, and this tetrahedral intermediate actually shows that for every negative charge there has to be a counter ion, so the magnesium is going to be next to the negative oxygen. There are no good leaving groups in my tetrahedral intermediate, so the oxygen picks up a proton from the acid at the end of the reaction, and I get, in this particular case, I get a secondary alcohol. Anytime you attack an aldehyde with a Grignard, you're going to make a secondary alcohol. If you attack formaldehyde, that's going to produce a primary alcohol. If you attack aldehyde, secondary alcohols. And if you attack a ketone, you're going to get a tertiary alcohol out of that reaction. All right, let's do a couple of problems in here. Let's attack formaldehyde. Formaldehyde is your most simple aldehyde, and you can attack it with Grignards or organolithiums. So I'm going to use phenylmagnesium chloride. And again, the carbon that's attached to the magnesium, this is a nucleophilic carbon. So it's going to attack the carbonyl, form a tetrahedral intermediate. And the tetrahedral intermediate, I have two hydrogens attached to it, to the carbon. And I just attached a benzene ring to it. It doesn't have any good leaving groups. It has two hydrogens, terrible leaving groups, and a phenyl group. It just came in. Let's not kick it out. So when you quench the reaction, when you're working it up with water or maybe hydronium, the oxygen is going to pick up the hydrogen from the water, and that's going to give you your, in this case, primary alcohol. If you take a ketone, let's take 2-pentanone, and let's use an organolithium for variety. So we are going to use methyl lithium. So you add methyl lithium to it, and then you go ahead and you add water to the reaction. But the methyl is going to attack the carbonyl, form your tetrahedral intermediate. I just added a second methyl, so now I have two methyls. My oxygen is negative. No good leaving groups. Carbons are not leaving groups. So when I add the water, that's when the hydrogen picks up the hydrogen right there. The oxygen picks up the hydrogen. And this one right here is a tertiary alcohol. So whenever I attack a ketone, I'm going to add a third carbon group to the carbonyl, and I get a tertiary alcohol out of that reaction.